Welcome. We're going to do 8-in-1 lesson 13. This is the last lesson of unit 1. Last unit of 8-in-1. This is comparing numbers in scientific notation. We're going to do something that's, I think, a little on the maybe the easier side, which is actually comparing those numbers. And then we're going to turn around and we're going to try and prove it. And we're going to use an informal proof. We don't need to do formal. I don't think we need, we're going to do formal proofs here in 8th grade. I think just understanding just kind of how to show something with numbers in math without all the formal rigmarole is probably more useful. Hopefully that's good enough for you, good enough for your teachers, but that's the way we roll. Okay, let's cut over and let's get into the lesson. We're going to bring up our magic board here, and we're just going to look. No, we're not going to start here. This is where we will end. We're going to start instead with simply how to know what number is bigger. If we have two numbers in scientific notation, and let me just put up a third one here. I'm going to put up a third one just because I was thinking about this. Or just a second. Let's come up with a number here. Okay, yeah, let's do that one. Okay, so we're going to look at which is bigger between two numbers written in scientific notation. And remember our rules here. If we have two numbers, comparing numbers in scientific notation. Okay, so if we have two numbers written in scientific notation, we know that A and B have to be between 1 and 10. And B has to be between 1 and 10. Okay. All right, so here we have an example of a number in scientific notation. In this case, we have 2.1 times 10 to the third, or 9.3 times 10 to the first, and we're just asking which is bigger. So let's just convert these numbers first of all. And I'm going to do the conversion. And we're not going to show you how to do the conversion because we did that already back in lessons 7 and 8. So what number is bigger? I've converted these two numbers, and we see that the first number is bigger. So in this case, we have, let's go to a different color here, and we're going to say that this one's bigger. And we'll do the same thing on the second one. After we do all five, we'll do these first A through D. And then we're going to come up with our rule. This is 0.99. And this is 10. So in this case, we have this second number is bigger. Okay, and let's go on to this third one. And this is 5 times 10 to the fourth or 5 times 10 to the third. I think we have a sense probably that this first one is bigger, but we'll go ahead and write them out. And we will circle that one. And we're going to do our final conversion here, which is 140 or 520. And in this case, our bigger number is this second one. Now, we're converting, in this case, I've just started off by doing the conversions back to regular numbers because we know how to compare regular numbers. And then we're going to come up with a rule in scientific notation for comparing numbers, and then we won't have to do these conversions. So let's look here and let's see what is true about each one of these, at least A through E. In this case, we have the bigger number is the one, not with the bigger first part, but the bigger exponent. So the first thing is the first rule, and I'll write this in the middle, a number in scientific, okay, let's write this again. In scientific notation, a number is bigger if it has the larger exponent. So that's rule A, right? So let's look at that. Here, the first one has the larger, on A, we have a larger exponent of 3, and that makes this number the bigger number. In case B, 1 is larger than -1, so the second number is the larger number. In case C, the first number has the larger exponent, and so that is our bigger number. So see, and you can kind of get a sense of it. The power is more important than the first part of the number in telling you how long this number is going to be, or how many zeros it's going to have after it. You kind of can get a sense of that. Now, we're going to use this rule on the second page when we do some more examples. Now, in this case here, we have two numbers that have the same exponent. So in this case, B, if the exponents are the same, look to the first number, right? So in this case, 5.2 is bigger than 1.4, so the second number is going to be the bigger number. If you take 5.2 and multiply it by 10 to the anything, and you take 1.4 and multiply it by 10 to that same number, this number will always be larger. Now let's use our rule here on this next one, and let's see let's not make a mistake here. Well, our rule here would say that this second, and this is a trick question. This is a trick question. So I'm going to let you think about this one. And maybe you can convert it and see that the rule doesn't apply, and maybe you can tell me why. Okay, so hopefully you've looked at this one, and now you can come back and you can see that this number here is 5240, and this number down here is 1200, and this first number is bigger. This first one is bigger, and you're like, wait, we just learned this rule that said we look at the exponent, and if the exponent's bigger, then the second one's got to be bigger because it's got a bigger exponent. Well, what's the problem? What's the trick? What trick did I play on you? Well, the trick that I played on you is that this number is not in scientific notation. This is not in scientific notation. Whoops, what did I do? I misspelled the word notation. So remember, the rule when you compare numbers in scientific notation is that both numbers have to be in scientific notation. This number is too large. Okay, so now that we got the rule, first look to the exponent, then look to the coefficient if you have to. Let's see if we can apply that on this second page. Now I took these numbers are the mass. Let's look at just the mass. We're just going to look at the mass of these various planets. And I got this from Wikipedia. Here's my reference. I took this off wikipedia.org at Wiki in the Planet Mass. You know, it's very important when we take things from the internet that we cite our references, references. Okay, now, what is bigger, Mercury? What planet is bigger, Mercury or Jupiter? Now let's look at Mercury. Mercury, I'm going to just kind of round these. 3.3 times 10 to the 23rd kilograms, or Jupiter, which is 1.89 or 1.9 times 10 to the 27th kilograms. All right, I'll let you think about it. And tell me why. Make sure you understand why. So pause. Okay, now you're back. And the answer is Jupiter. So give yourself, if you said Jupiter, give yourself a happy cat if you said Jupiter, because the answer is, which is very important, why? It's because 27 is bigger than 23. So if we wrote these out as numbers, you would find that Jupiter would have a much bigger number because 27 is greater than 23. All right, let's do another one. What is bigger? Saturn or Venus? So Saturn is, and I'll let you figure this out, and you're going to have to copy it over yourself. Do all the work. Okay, pause and come back. So let's see what our answer is. I'm assuming you thought it out. This is 5.7 after you round it times 10 to the 26th. And Venus is 4.1 times 10 to the 24th. And so our answer is Saturn because 26 is greater than 24. All right, let's do one more and let's compare Saturn or Neptune. Okay, Saturn is 5.7 times 10 to the 26, as we just learned, or Neptune, which is 1.0 times 10 to the 26. These are both kilograms. So form your opinion and come on back. Well, the first thing we do is we say, well, 26 equals 26. So we can't look at the exponent, so then we have to go to the coefficient. And we say, well, 5.7 is greater than 1.0. So Saturn is bigger than Neptune. So think about if you had to write out Mercury, you know, it would be 33010, and we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. We'd have, this would be the mass of Mercury. And then remember, this is why we don't like to represent these kinds of numbers in just regular format. It's much easier to write and compare numbers that are in scientific notation. That's why our scientists are smart, and they figured out this easier way to write, not only write numbers, but to compare numbers. All right, now those, hopefully this is not a hard, this is kind of an easy rule to learn, and an easy, not just an easy rule to learn, but an easy concept to understand. And if you understand the concept, we're going to just give you a big happy cat, and we'll spin them around, and we'll move on. Now, this is kind of a harder thing to do, these proofs. And I'm just going to I'm not going to do a proof, a formal proof, as it were. I'm going to do one that I think is good enough, but also is one that you can understand. Because proofs, when they get really technical with their notation and stuff, can kind of get hard to understand. So let's look at the two cases that we have for comparing numbers in scientific notation. So if x equals y, so let's look at the example here where x equals y and 10 and a is greater than b. So we want to prove that, well, let's take a step back. We want to prove that if two numbers are written in scientific notation, then let's see, two numbers, and I'm going to go back and write the rule. Written in scientific notation. We have case A. We have case A that says if the exponents are the same, then compare the coefficients. Those first numbers. B, if exponents are different, then compare the exponents to see what's bigger. ... to see which is bigger. So let's start off, and we're going to, undo. Okay, so we're going to start off, and we're going to try the case, and we're going to say, this is the case A when the exponents are equal. Okay, so that's part A. So we're going to say A times 10 to the y to the x, and we're going to compare it with B times 10 to the x. Okay, so what I'm saying is that if the exponents are the same, you just simply compare the coefficients to see which is bigger. Okay, so let's take this to the next step. So we're going to divide. In this case, we're going to divide both sides, and kind of the question is how to compare them. So we have these things on a balance, and we want to see which one is bigger. And so now we're going to say, well, this is B times 10 to the x, and we're going to divide both sides by 10 to the x. And so if we divide both sides by 10 to the x, on the left side we have A, and we want to know how that compares to B, because these things cancel. Well, if you're comparing A or B and you want to know which one's bigger, you just simply say, well, which one's bigger? So this is just kind of an informal proof. So if A was bigger than B, then A would be, you'd just say A is greater than B. You'd say if A is greater than B, then A times 10 to the x is greater than B times 10 to the x. If A is less than B, then A times 10 to the x is less than B times 10 to the x. And then if A equals B, then A times 10 to the x equals A times 10 to the x. Okay, so that's kind of the easy case if the exponents are the same. Now we have to prove when the exponents are bigger. And so this is good. This is a little bit more, have to be a little bit more formal. So, well, let's put our happy cat down. Happy cat. Now we're kind of out of room here, so I'm going to need to, let's see, we're going to make a new page. Open, we're going to duplicate this page, and then we're going to open it up, and then I'm going to undo all of it. Well, we'll just erase it. We'll just erase it. And so now we're going to go to case B. And these are informal proofs. These aren't, this isn't for, college students. This is for, 8th grade students that are just trying to understand. So if we have A times 10 to the x, and we have b times 10 to the y. And I'm going to start off, and I'm going to say, let's just assume x is greater than y. So if x is greater than y, that's what my rule says, then a times 10 to the x is greater than b times 10 to the y. And that's what I'm going to try and show. So if x is greater than y, then I can say we're going to try and compare a times 10 to the x, and I want to show that that's greater than b times 10 to the y. Okay, so if x is greater than y, one thing that I can do is I can divide both sides by 10 to the y. And that's a positive number. So I'm going to divide both of these by 10 to the y. Whoops, not 10y, 10 to the y. So on the left side here, I have, remember, I have a times 10. And this is by my exponent rules. I have 10 to the x minus y. And on the right, I have just b times 10 to the 0. Right? Y minus y is 0. And we know that 10 to the 0 is just 1. So I have a times 10 to the x minus y is greater than b. Now we're almost there and able to show that this left side is greater than this right side. Well, we know that b has got to be less than 10. This is by rule. You know, by rule, when we start off, and if this is in scientific notation, then I know that b is less than 10 and it's greater than or equal to 1. So I know that b, by rule, b is less than 10. Okay, now let's look and analyze this left side over here. Well, I know that a is at least 1. And 10 to the x minus y. Now, if x is greater than y, then I know that this exponent has got to be positive. If x is greater than y, let me write that over here on the side. If x is greater than y, then x minus y is greater than 0, right? If I subtract y from both sides, I get on the left side here, I get x minus y, and on the right side, I get greater than 0. So if x minus y is greater than 0, then 10 to, then that number's positive. So 10 to any positive exponent is got to be greater, and that's and it's an integer. It's not only a positive exponent, but it's a positive integer. So the smallest positive integer would be 10 to the 1, but it could be 10 to the 2 or 10 to the 3. So 10 to any positive exponent, it is greater than 10. So 10 to the x minus y has got to be greater than or equal to 10. So the smallest number is 10. So the lowest this can be is 10. And then this is at least a 1, right? Because the rule is that the coefficient has to be at least 1, but not less than 10. So if you think about it, a number that's at least 1, the lowest number is 1, and I multiply it by a number that lowest can be 10, the lowest that this can be over here is a 10. And if the lowest that this can be is a 10, this is the least. This is the least it can be. And if the right side is less than 10, then I know that this left side is greater than this right side. So that's kind of a very informal proof. If we start with a times x to the 10 A times 10 to the x is greater than b times 10 to the y, and x is greater than y, then we know that this left side, after we do this division, and then we continue on through, that the left side is still going to be greater than the right side. And so you can just simply compare exponents. Okay, so coming back to our Hangout, our Google Hangout, we can wrap up this lesson and say, well, the key thing from this lesson is to remember the rule about comparing scientific notation. The proof that I did is a little bit informal, but it's meant to kind of give you a sense of one way that you can show it. Maybe a little confusing, but this wraps up 8M1, Unit 1 for Engage New York, Eureka Math, Unit 1. We're going to move into Unit 2 with the next videos, and hopefully you were with me. Hopefully this was helpful. Let me know. Definitely sign up for, or at least subscribe to this video if you liked it, or this playlist, my channel if you liked it, and let me know if there's anything I can do better. Thank you very much.